Hello everyone, I'm Giuseppina Andresini, and with my colleague Gianluca Zaza from the University of Bari, we present a poster entitled Harnessing Explainable AI for Enhanced Image Processing. The topic of this poster is related to the emerging research trend of Spoke 6 of FAIR on symbiotic AI that focuses on the design of intelligent systems that can collaborate with humans to become more understandable, fair, and transparent. In particular, a critical aspect of symbiotic AI systems is the need for explanation. This is also a key feature in image processing, since it provides a useful tool to create visual explanation of model decisions that can also help to identify biases and errors in the model. In particular, several XAI approaches have been considered in image processing literature in several fields. One example is in the cybersecurity domain, where we explored how XAI can be applied in a deep learning process for cyber-free classification, with the goal to improve both the accuracy of the model and the explanation of data. To this aim, we formulated an attention-based deep learning approach that combines knowledge distillation and XAI. This architecture learns a teacher-student model where the teacher is implemented with a vision transformer and the student is implemented with a convolutional neural network. Specifically, in our work, we propose a revised version of knowledge distillation strategy where we use the explanation extracted through the self-attention layers of the VIT to distill knowledge in the student learning. More in detail, the teacher takes as input an image representation of the data and extract explainable imagery signature of data. And these explainable signatures are used both to improve the model's performance by guiding the student learning and also to extract useful information from data classes. In fact, in the experimental study that is reported in the original contribution of this work published in Computer Security Journal, we proved the effectiveness of the approach in multi-class classification, as well as how the explanation can be used to extract useful patterns of data classes. For example, in the malware detection task, we show that the attention maps extracted using the VIT highlight that the feature pwrite64 and fdatasins are important to distinguish malware application to benign application.
The second project utilizes a graph neural network to segment the brain tumor images. This work is possible to divide into four main steps. The first part involves acquisition and preprocessing of MRI images. As can be seen, we have different modalities of MRI images along with the corresponding ground truth image that identify the segmentation. The next step is to construct a graph representing the underlying brain connectivity patterns and concatenate the four MRI modalities of the dataset to generate a single cohesive three-dimensional image for each patient. Once the final MRI image is obtained, the simple linear iterative clustering algorithm generates a set k supervoxels. It uses a k-means approach that groups voxels based on their physical proximity and their brain's intensity values. Then, supervoxels located outside the brain mass are filtered out, and the remaining supervoxels are assigned a feature vector based on the intensity values derived from the consequent voxel across all four modalities. Subsequently, each supervoxel is represented by a 20-dimensional feature vector and assigned a label based on the most frequently occurring label of its constituent voxel. Once the supervoxels are generated for each patient sample, they are used to construct a graph. In the third step, you can see the final results of graph representing the brain. Each node represents a specific area of brain. The red nodes represent enhancing tumors. The blue nodes represent necrotic tumor core. The yellow nodes represent edematous tumors. And the gray nodes are another brain area. As you can see, each node is interconnected with the other. Thanks to the preprocessing phase, you obtain 50,000 nodes in total. Finally, in the fourth step, you can see the final results of pipeline, which show the segmentation of different tumor areas of the brain. Thank you for your attention.